All right, so last thing we've got to talk about is deciding if a piecewise function is continuous or not. Deciding if a piecewise function is continuous. So when we see our rational functions, those are our functions that could have infinite or removable discontinuity, right? Those are our holes in our asymptotes. They're just a fancy word for holes in asymptotes. Our piecewise functions are the ones that can possibly have jump discontinuity, because those are our pieces where they possibly could be separated right along that fence that we draw. So we basically are going to be checking to see if they're coming together at the same point, or are they two separate graphs that aren't connected. That's all we want to know. So just to make sure we're really good at this, we can always also go back and draw ourselves a graph if we're not sure, if we want to check if it has jump discontinuity. We can always get ourselves a picture because that's the easiest way to see it. So if I'm going to graph this, I need to make two tables, right? Make an XY table for x squared, and I'm going to make an XY table for 10 minus x. They're both going to start at 2, since my inequalities or my bounds are x is less than 2 and x is greater than or equal to 2. Since x squared is numbers less than 2, I'm going to go 2, 1, 0, negative 1. 10 minus x is numbers greater than or equal to 2. So I'm going to 2, 3, 4, and 5. And then I'm going to plug in. So when I plug in 2 to x squared, I get 4, 1, 0, 1. When I plug in 2 to 10 minus x, I get 8, 7, 6, and 5. And then I just plot those points. I can see that x squared is not equal to, so this is going to get an open circle. This one is equal to 2, so that one's my one that's getting a closed circle. Go ahead and draw my x and y axis. I'm going to put in my fence at 2. And then I'm just going to plot my points. So I get 2, 4, 1, 1, 0, 0, negative 1, 1. And then I also get 2, 8, which is lovely. Doesn't fit on my graph, it's all the way up here. 3, 4, it's like up here. Coming down. 1, 2, 3. Good thing I'm good at using my imagination. So all we're going to be doing today is deciding if that function is continuous or not. So if you draw yourself a picture, you can clearly see, are those two pieces connected? No. I can also tell before I even graph it if they're going to be connected, because in order for them to be connected, they have to have the same y value. So what we're going to do in order to decide if a piecewise function is continuous, we're going to first look at the two pieces of the function, make sure the two pieces don't possibly have a hole or an asymptote. Then we're just going to look to see that when we plug in the bound, we get the same y value for both of them. Because as long as we get the same y value, then those two pieces are going to meet, and we'll be good to go. So knowing what this graph looks like, if I ask you to determine if that function was continuous, there's like a little checklist that we're going to go through. So the first thing I want to know is I want to ask myself, is x squared continuous? And if I look at x squared, am I going to have any holes or asymptotes in x squared? Do I have any factors that cancel out? Do I have any factors in my denominator that don't cancel out that I can set equal to 0? I don't even have a denominator, right? I also know x squared is just the shape of a parabola. So I know that x squared is continuous. Yes. Then I want to know, is 10 minus x continuous? And the reason I'm asking myself this is because if the pieces aren't continuous, then I don't even have to do the work to check if the entire function is continuous, because if one of the pieces isn't continuous, then the whole thing can't be continuous. So then I have to ask myself, does 10 minus x have any holes or asymptotes? And same thing. I know that 10 minus x is just a straight line. It's a linear function, right? Linear functions are continuous, so yes, this is continuous. If I had gotten no for either of those, I would already be done, and I could say no, the function is not continuous, and move on. Since they're both continuous, I want to plug 2 into both pieces and see if I get the same number. Now, we already graphed this, and we know we're not going to get the same number, so just to make sure, the third thing I'm going to do, plug in bound to both and see if the y value is the same. So I'm going to take x squared, and I'm going to take 10 minus x, and I'm going to plug this 2 into both of them. So I end up with 2 squared and 10 minus 2, which gives me 4 and 8. And in order for it to be continuous, they'd have to be the same number. Since they're not the same number, it's not continuous. No, the function f of x is not continuous. So check both sides, and then check to see if they give you the same output when you plug in the bound. If you get yes for all of those, then yes, it is continuous. If at any point you get no, you can stop, and you don't have to continue on because you already know it's not continuous. Let's try one more, just to make sure you're super ready to rock and roll, and then later classwork on the way. So if I give you f of x equals x plus 2, when x is less than or equal to 1, and 2x plus 1 when x is greater than 1. And I want to know if it's continuous. We've got to first look at the two pieces, and then we've got to plug in. So this is where our parent functions definitely help us out, because if we can recognize our parent function, we know that which ones of those have asymptotes, which ones of those are continuous. So when I see x plus 2 and 2x plus 1, I know both of those are linear functions, right? Linear functions are continuous, so I'm good. Both pieces are continuous. I just need to know that when I plug in 1, so when I take x plus 2 and I take 2x plus 1, and I plug in 1, I end up getting the same number, which means that both of these pieces, as they approach each other, are going to come together at 3. They're both going to have the same y value, so they're going to meet, and this is going to be a continuous function. I think we're going to be rock stars at this, right?
Wait, how do you figure out, like, in the first one we look at x squared continuous, how do you figure out if it is?
So the easiest thing for me to do is look at the parent function that's in there, right? So x squared I know is a parabola, and we know the shape of a parabola is that smooth U shape. The whole thing is connected, so I know it's continuous, because I already knew what a parabola looked like. I also know that I'm only going to have holes and asymptotes when I have rational functions, which x squared isn't a fraction. There was no denominator, so I'm not going to have a hole, I'm not going to have an asymptote, so I didn't have to worry about any of those. It had to be continuous. So then same thing, the other ones were all just x plus some number, which makes them a linear function. Linear functions are all our straight lines. They might be moved up and down, they might be tilted a little bit, but they're all going to be a straight line, so those are all continuous as well.